Hello sapiens. Today I'll be talking about convergence. There are two convergence which are common in probability theory. The first one is called almost sure convergence. Almost sure convergence. And the second one is called convergence in probability. So what I'll do in this video is I'll give a motivation for each of these definition. Almost okay, the spelling is like give a motivation for each of this definition and just try to get a feel on how they differ and hopefully also an example. So let's begin with almost sure convergence. Almost sure convergence. So suppose I'll first give you an official definition and then I'll give an intuitive understanding. So suppose you have a sequence of random variable xi, then we say xi converges to a random variable x almost surely if all these random variables are defined. The domain is the probability space, which is omega, f is the sigma algebra, and mu is the probability measure. So when we say this converges to this, what we are saying is consider the measure of this set x such that limit I tends to infinity xi of I should not use x, I should use omega, which is a standard notation for elements in this space, small omega, equals to, not equals to, or equal to anything. We can change accordingly the condition. So this is a set. Consider all x so that this limit is not equal to this. The measure of that set should be equal to 0. If it would have been equal to, then this would have been 1. This is a definition. Now the second definition is convergence in probability. So again consider a sequence of random variable and we say x converges to x in probability if first fix an epsilon greater than 0, and then we say that the limit of this set omega such that xi omega minus x omega is less than 0. I say less than epsilon. We'll go with this one. So suppose this is a set suppose this is a set then let's denote this as, if you take the limit I tends to infinity, this should equals to 1. So what is this saying? And this should be true for all epsilon greater than 0. True or false for. So what is it saying? So I can think of a set B for fixed epsilon. I can think of Bi as omega such that xi omega minus x omega is greater than epsilon, is less. Okay, I'm working with less, so it's less than epsilon. So in some sense it is close enough to x. So if we are imagining it to converge to 0, when we could this condition looks familiar, that it is coming arbitrarily close to this. So for a fixed epsilon we'll look for I, for each fixed I we can look what is the set, we can call it as what is the membership, what is the structure of the good set. These elements are good because these are helping in convergence. So this is a good set, so I can call this as a good set. The probability of this good set should go to 1, should go to mu of Bi should go to 1, limit I tends to infinity. Okay, so a vague shortcut way to remember the difference between these two definitions is the limit occur inside of this, and this is like exactly and here the limit occurs outside of it. Also there is a subtle difference in the condition that's mentioned. Here the set is defined in a very crisp manner, that is the limit equal or not equal. Here we are going in the epsilon delta domain, that okay, is it close enough for each epsilon and all that. So if this holds true for all epsilon, the limit is goes to this, and this is convergence in probability. Now let's understand in the intuitive meaning behind this. So for a moment, forget about probability theory. Just try to recall. Just try to interpret it in terms of measure theory. So because probability is a measure on 0, 1 interval. So let's just recall what was in if you think it is normal measurable function, then just try to recall what is pointwise convergence. So pointwise convergence. So we say for the sake of familiarity, we'll just use xi as a function here so that it matches up with the random variable. So we say, suppose there's a sequence, and we say xi converges to x pointwise if xi omega limit I tends to infinity equals to x omega for all omega. This is the condition of pointwise convergence. Fine. Although it's unrelated, this fact is unrelated here, but one could show. One could show that pointwise is same as uniform convergence for measure theory in certain measure theoretic sense. I might mention that soon, that fact. Okay, so this is a pointwise convergence. Now suppose suppose xi does not converge to x pointwise. Okay, so let's not diagnose the problem. What is the problem? So diagnose the problem. So consider a special situation where a specific example where we can partition omega into omega 1 union omega 2, where if omega belongs to omega 1, then omega 1 belongs to omega 1, then limit xi omega goes to x omega. So then we can say that xi converges to x not on omega but on omega 1 in a smaller set. So we have identified the problematic part, that omega 2 was problematic part. Now if it turns out that the measure of the problematic part is 0, then we can weaken our notion of pointwise convergence by saying that it converges pointwise in omega. Because when we say some set has a measure 0, we mean to say that it's a very negligible set. And if we are doing any operation with respect to integral or any such thing, we know that measure 0 set really means negligible set. It has 0 value and all such things. So one trivial example would be that suppose a function defined on R is almost pointwise convergence, just it's not satisfying that value at few finite values of finite points in domain. So you can feel like okay, just ignore those points, and they don't have much weightage. So this is just general capturing that notion. So therefore it's appropriately called almost surely, that it's almost there. The parts at which it is not there, it has measure 0. So I think this is a very fair generalization of pointwise convergence. We can say something converges pointwise if it converges pointwise on a measure 1 space. Now the next one is slightly tricky. I found it very tricky. Tricky if you interpret it in this way. Again, let's divide. So again, we're interested in pointwise convergence. All right. So xi, pointwise convergence of xi converge to x. So now omega can be divided into omega 1 union omega 2 as previously, and omega 2 can further be divided into omega 2 1 and omega 2 2. So I'll just tell you what it means. So just to recall, omega 1 is basically limit x of xi of omega equals to x of omega I tends to infinity for all omega in omega 1. So if so this essentially, if you're fixing omega, this essentially becomes a sequence. So xi omega becomes a sequence. Xi omega becomes a sequence, is a sequence indexed by I, and it says that it says that its limit is x omega. So now there are two possibilities that so it means that in omega 2 sequence does not converge or converge somewhere else. So what I mean by that, so omega 2 is the set where this sequence, let me write it again, xi omega converge to c, which is not equals to x omega, say. So all such points are collected in omega 2. Now what are the points collected in omega 21? They are points, so the sequence, this sequence, this is more like a non-convergent sequence. It's like an oscillating sequence, so there is so this kind of thing. So even among them, it's not that all such sequences are present in omega 21. We could think of this as these are the kind of sequence which are not converging. It oscillates but has a subsequence which converges to our point of interest. So it may have, it does have, not may, it does have a sequence, subsequence actually, which converges to x omega. So a trivial example would be c x omega, this kind of sequence. So you can see that okay, this sequence does not converge, but in still loose sense there is a subsequence which is the object of our interest. So this particular situation is interesting, so we are setting it aside and capturing it separately in omega 2 of 1. Now we want to look at, okay, how to make sense of it, how to reasonably loosen the justification. So it's not just any subsequence will work. What we require is that this should dominate the sequence, in the sense that there should be more of this in the sequence and less of this. So the gap, so it's like almost almost all the subsequence, if you choose any subsequence random, it should converge to x omega than to c. Then we can say that okay, this is not a convergent sequence, but if you weaken it a little bit, more often than not, it will give you a random, if you give you the subsequence which converges to r, if you choose it. And by choosing I mean choose by underlying probability. So underlying probability. So basically what we require is that all this c, even though it occurs infinitely many times, it should occur at the gap between these two should always widen up, and so that the ratio tends to 0. So this is the intuition behind it. More formally, what you can write it here is, omega, this is still not sufficient, but this is a necessary condition to, so omega 2 will contain, we want to may have a collection of such sequences in omega 21 such that this property should at least hold. Now we want further more properties. So suppose there are multiple omega, so each omega will give you a sequence. So let me call it omega 1. It need not be countable, but I am just writing it just for illustration purposes. So it will have, so I will just use for right to mean that so basically this will have some sequence, another one will have sequence. I could say that at any instance, if I pick up, at any index I pick up, there will be long sequence. The towards the infinity, because we are interested in convergence. So at any individual sequence, the value attained at infinity could be because it's not converging, so essentially we're looking in the domain of lim sup or anything in between which is permissible. So more or less the value will not be suitable. So by requiring that this dominates, it is most likely that we'll have a suitable value here. But we just don't want to be satisfied with that value here. What we want is this to hold true for all the other sequence, for all different omega 1. So this is a sequence corresponding to omega 1, this is a sequence corresponding to omega 2, this is a sequence corresponding to omega 3. So if at say infinite position, the most of the big sequence has the right value that we are looking for. So it's like x omega 1, x omega 2, dot 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 x omega 3. Maybe one or two will not have the right value, but the proportion should be in favor of this kind of thing. And this proportion at infinity, so we can call this as the right term, and the one which is not equal to the desired term, we can call it wrong. So the proportion of wrong or bad, and the proportion of that bad should progressively decrease. Then it is then it is desirable if that happens. So we can say that okay, then if we go back to our intuition, then we can say that okay, this is this one at this point, it is not pointwise convergence, but when looked at this, when these bunches are looked together, they are like they are almost like most of them are converging, and the convergence will only get better and better as you go deeper and deeper into the index. Okay, so just I had previously, so this was about collective property of all the sequences. So an implication would be that if you focus on one individual sequences, the right at infinity, so if you take infinity as a number, suppose it starts from here, just for the visualization, the proportion of the right answer should dominate the proportion of wrong answer. This in itself is not sufficient, but it's a necessary condition. This entire, the collective ratio, the collective proportion is the necessary and sufficient, and as a consequence, if we get that if we focus on one, the proportion should be in favor of the right answer. So this is again intuitive, as I previously mentioned, because you're imagining that okay, this is not pointwise convergence, but it's just giving me answer occasionally wrong. So this is almost like acceptable. We don't mind it that much. This is again a weaker notion. So a further weaker notion, and this is what exactly convergence in probability means. Convergence in probability. And as you could have just seen by my motivation, that almost sure implies convergence in probability, but not vice versa, because here omega 2 equals if measure of omega 2 equals to 0, then here also it's 0. But if omega, here you need 2 equal to 0, but 1 need not be equal to 0, and hence omega 2 need not be equal to 0, and hence we don't have the reverse. But just as if you look in my explanation, I was kind of hinting towards a proper subsequence. So if you can suitably choose a subsequence, so earlier the explanation was that at infinity it almost behave well except for a few points, but if I am allowed to choose a subsequence, I can always choose to ignore it, and in that case the converse holds true, that from probability you have almost sure convergence. From probability in convergence in probability, almost sure convergence. Yeah, because you can always make this term 0. Okay, what I have said so far might seem to be a little too abstract. If that is the case, I think this example would help out. So consider this function. So first choose some n, fix n, then partition it into such that many intervals. So there is like in partition 0. No, let's just start with 1. Partition 1, partition 2, partition 3. For a fix n, you can partition interval 0, 1 to partition 1, partition 2, dot 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 partition n, and then you can consider n functions here. n functions. The functions are like any kth function would be 1 here and 0 outside. So essentially I am having a sequence. So basically if I have to write it, I should write it as Fij. So first I have to mention what is the partition. So that will be taken care of by the ith term, number of partition, and j is referred to the exact partition. So if I say 10 divided into 10 parts, so I will divide it into 10 parts and I refer to, okay, look at the sixth part. So and then once you have chosen that, then the function that you choose is the indicator function, that it's 1 there and 0 elsewhere. So this gives me a sequence of function, actually double sequence of function Fij. Since both of them are individually countable, the entire thing is countable, so hence it could also be treated as a sequence. If we treat it as a sequence, you have to mention ordering. So mention ordering. So ordering will be like this. So we'll first go towards increasing n, and for tie, if it is a tie at n, then increasing k, where k is the partition number. Partition number, and here is the number of partition, and is a ठीक. So I think this is intuitively clear. Now I will show that this sequence, what's called Fij, converges to 0 in probability, but not almost surely. Let me write it as g of k, g of v, say, because I'm writing it as a single function. So we will take 0 to infinity. So to show that it converges in probability, what I need to show is fix epsilon. Say epsilon I have fixed. Then I have to show that Fij omega minus essentially it is just this one, because the limiting point is 0 itself. So if I consider this set, not again, I have to keep reminding myself that I have to change the indentation. This is a set for a figure. So so as you could see, this refers to some indicator function, small indicator function, and I know that this interval, because n is increasing, will shrink. So for a given epsilon, if you fix an epsilon, then after long enough v, this will shrink, and so it will be 0 outside, and it will be 1 here, and the set, the measure of mu of bv of 1, it will be like, the width is like, if you partition into 1 by n, so 1 by v, which I can choose v small enough to be less than epsilon, and hence in the limit, sorry, I misspoke. So it at this interval it will always be greater than epsilon, but I can smaller the width. So what will turn out that the width will get subsequently smaller, so this measure will be 1 by mu. So and hence in the limit, this will tend to 0. So this converges in probability. Alright, and this is true for all epsilon. Yes. Okay. Okay. Now, but I will show that this is not convergence. This it does not converge almost surely. Now the reason for that is, for each omega attains 1 infinitely many times, because this omega this omega will contain this partition, then a smaller partition, and then a smaller partition. It will never end, so it will attain 1 infinitely many times. So the any sequence, say gv of omega, if you consider this sequence by indexing v, will not be a convergent sequence. will not be convergence sequence, and hence there is no point of pointwise convergence. Therefore, as a whole, it will not converge almost surely. So I hope my explanation might have made the concept of almost surely and convergence probability a little bit clear. Thank you for watching. See you later. Bye.